Okay, guys, we're going to do a problem real quick. In the diagram below, a toy car has a mass of 2 times 10 to the second grams. Now, important to realize it says grams. And let's zoom out just a little bit. And travels 6.5 meters along a uniform track until it comes to rest at point B. So it's going to start here at point A, and it's going to travel to point B. And this is going to be cool. And at point A, it has a height of zero point 0.7 meters, and at point B, it has a height of zero point 0.2 meters. Now, the important thing here is to realize that it's at rest at point A, and it's also at rest at point B. So that really means, guys, that there can't be conservation of energy. It must not be ideal. Because if it was ideal, this car would go flying off the ramp. It would travel down through here and go and fly off and land over here somewhere, you know? But it doesn't do that because we have friction. These surfaces cause it to slow down and lose energy. So the main thing we need to figure out is how much energy is lost. And also, what is a loss of energy? Well, a loss of energy is a change in energy, and that's what we call like a loss or a change. And it's going to be our energy final minus energy initial. Now, in this problem, realize that we start off at A and end up at B. So these are actually going to be EB minus EA. And that's going to be our delta E. Now, the other thing to realize is this, is that we're going to have another, well, it asks us to find here, let's actually just keep going, Mr. Shaw, let's not stop there. It says calculate the magnitude of the frictional force. So we're looking for the frictional force. Now, this one is a little confusing, and it does deviate a little bit from what might be intuitive. But we need to realize that, remember, work equals delta E, but also work equals force times displacement. And it may not exactly be the displacement here we're looking for, but we're actually going to use this distance number to fit in. This is going to be our distance. Okay, so this is, yeah, let's put it as displacement. But in this case, we're going to use a distance number there. Now, what happens as this object goes down, you know, we can actually just keep calculating for every minute fraction of a second. We can calculate how much energy we've lost to force. And you notice this thing is going to change directions. So it is a little bit different. If you get really meta and you think really deep about it, you can say, well, Mr. Shaw, this formula, the displacement should be a straight line, and the displacement should be a straight line from here to here, and that's the number I should use. Now, there's no possible way for me to find that number, but what I'm asking you to do is instead think of this. Think of just a small distance. Let's change so we have a color. Think of just the smallest possible distance, like that right there. If you hopefully you can see that. Think of that area right there. And think if we just keep doing that again and again for every small increment. And then after we do that, we add that up. Now, we would cover the entire distance of this track. So we're going to use the distance value. Okay. Hopefully I haven't lost some of you guys. And I'm going to go into doing the nuts and bolts of things. Well, remember, guys, we're talking about a change in energy. Now, the only information this problem gives us, it doesn't give us anything about kinetic energy. Well, it does actually. And it tells us that our kinetic energy there is 0 and the kinetic energy there is 0. So if your kinetic energy, for your total energy, I'm not using what I want. If your total energy is minus kinetic energy, you're just going to have for your EB, you're just going to have PEB. And for your EA, or your ETA, if you want to be very, very exact, you just have PEA. So I'm left with this. When I take this formula right here, let's see if I can move it. I'm missing a couple of things, but that's fine. I'll add them in a second. When we get down here, you can stop now. When we have this, now we're going to plug in these values. So what we get is our delta E is going to equal PEB minus PEA. And that's going to be equal to mghb minus mgha. And then simply you're going to remember that the mass is this value right here. And it's in grams, so you have to be very careful. I'm going to convert it in my head real quick. or actually, let's do this, 0.29 kg. And if you want to, you can combine like terms here. 9.81 meters per second squared. So these are my like terms. Do you see that? So I can rewrite this as mg hb minus ha. And if you look at your reference table, they actually deal with potential energy always as being changes. And it kind of makes sense, but it's kind of also annoying at times. And we have these h's up here, so it's going to be 0.2 minus 0.5. Sorry, I'm leaving my units off. I forgot them. I will put them down below meters and meters. So when we subtract them, guys, I think I made a mistake. Yeah, this is actually, no, it's not going to let me do it. This is actually the number 7. Sorry. So just plug this in your calculator, and this will get you your change in energy. Okay, not too bad. Once you've got it into your calculator, you'll get a value. And I'm just going to call that value, I'm going to say it equals x. So I've got this value x. And remember, x is the same as my delta E. And that equals work. And work also equals FD. So this force here, guys, when we look at this one, let me change colors to a more viewable one. This force, what causes this force? What's doing work here? Well, the work is caused by friction. That's what causes us to slow down. So that's our F of F. So we can just say F of F, divide both sides by D, equals whatever value you calculated here, divided by D. And that's how you solve it. Okay, thanks guys for listening.